All right, so how's everyone doing? I'm doing all right, doing all right. Midterm time, although that's not stressful for me or as stressful, but grading can be a pain. Um, okay, so today we're going to talk about stratospheric ozone depletion. We'll also do air quality lab check-in if anyone has questions. So we'll save 10, 15 minutes at the end for that, okay? Recordings, I fixed the one for 2/27, February 27th. So if anyone needs to go back and listen to that, it should be okay, or better at least. Midterm on Tuesday. So reminder about stuff. If you haven't turned in homework 1 through 3, you can do it tonight, right? Still get some points. The midterm, part 1 in class, no notes allowed, no calculations, 40 points. Part 2, I said it was going to be on Canvas. I changed my mind. It's now going to be a take home. Okay. So on Tuesday, I will hand you part 2. You will do it. You will return it on Friday at 2 p.m. Okay. You must do it by yourself, but you can use notes, slides, anything you want. Okay. At 2 p.m., I'll have a link online so you can do it via Canvas if you want, or you can just do it all, staple it, and put it underneath my door, right? If I'm not here, or give it to me, right? I'll tell you more about that. It'll actually be on the top of the test, okay? Study guides up here if anyone doesn't have it. Questions? Yes. I don't know. So part 1, I think actually it's maybe 20 or so. It will not take the entire class period, or probably won't, right? Most of it, you either know it or you don't know it, right? I would suggest, at least for part of it, I can, understanding what chemicals are involved in a lot of these things, understanding some of the reactions that we talked about, for like forming sulfate or ozone or whatever, those types of things, okay? Mechanisms, right? How we formed ozone, or how you go from a hydrocarbon to formaldehyde, something like that. Any other questions? Yeah. I don't think there's any multiple choice. I think it's all fill in the blank. There'll be stuff like, what process does this? What compound does this? Blank, and you'll have to know it. Anything else? All right. Okay, so last time we went through and we talked a little bit about like COVID and the reductions that we're seeing during the shutdowns, right? NO2, PM 2.5. I shouldn't call them shutdowns. People talk about that. We didn't really shut down here, right? But it was stay-at-home orders, right? The reason why we can't, it was totally different between what happened here and in China, let's say, right? Where it was, you can't leave your house, okay? Ozone actually went up in a lot of places. Why? Because if you reduce NO2, sometimes you could increase the amount of ozone. And then we talked about stoves. We kind of talked about the pros, cons, other things about gas stoves and banning them or reducing them, etc. Okay, those won't be on the midterm, okay, or won't be on any tests actually. What we're going to start talking about today won't be on the midterm, but it will be on the final, okay? So, the environmental movement, okay? You kind of think, if you think about the 60s, you think of like, peace, love, hippies, that type of thing, right? But that was also when the environmental movement started to develop, okay? I always, if any of you have seen like Mad Men, which is set in the 50s, 60s, right? At one point, they go to a park, they have their, their picnic, and they basically just, when they leave, they just leave everything behind, right? Now, you see someone do that, you go, what the hell is their problem, right? Things have changed, as far as litter. Why, they say don't litter on the freeway. kind of who would do that, right? But really, it was the environmental movement in the 60s that really started. Here's one example. The Cuyahoga River, which runs through Cleveland, actually in the 1960s caught on fire at time because of all the waste in there. Another example is a chemical called DDT, dichlorodiphenyl trichloroethane. It's over there on the right. You can see the dichloro and the diphenyl and all that. This was used during World War II and then after World War II. It works great at killing mosquitoes, etc. In the 1960s, Rachel Carson, she wrote a book called Silent Spring. And what it was, hey, you know what? If you're using this DDT, you can get what's called bioaccumulation and eventually bird deaths, and birds die, so you won't hear them, and therefore a silent spring. Okay? And then eventually could harm humans. Okay? And with the environmental movement, we started to realize that you can't just look at a chemical or a compound or whatever and just look at one portion of it. You have to look at its entire lifespan. Okay? They call it sometimes cradle to grave, right? So if you're using something, how do you extract the materials that do it, right? You mine stuff or what? How do you produce it? What happens during its use stage? And then what happens after it's used, right? What do you do with it? You just throw it out, or do you have to recycle it? You need to think about everything along the way, right? We talked, or I was mentioned about the Stanley, right? The Stanley mugs. There was that debate about the lead, right? And it's in there, and so it's fine, right? And that's true, and that's fine. But that's the type of thinking. We can't assume that everything is going to be used perfectly. Okay? You can't just say, well, during the lifetime, you have to look about the entire time. I'm trying to say here, here's an example of, battery electric versus internal combustion engines, right? So this is greenhouse emissions for different types of electric vehicles, right? And what you can see is, the smaller of the two, those are the electric vehicles. And the bigger of the two, those are the emissions from the internal combustion, right? And so in the US, you can see that, okay, going from internal combustion, which is what, if you have gasoline, to battery electric, you can see a huge decrease, right? Not to zero, because you still have to produce it, you have to maintain it, your battery manufacturer, you do get rid of this huge one, which is fuel consumption, right? The battery ones don't have that. But if you compare this to other countries, look at India. Comparing between internal combustion and battery electric, you don't see much difference. Why? Because their fuel sources are different, right? If you're burning coal to get that power, it's not doing any good. Okay, so that's an example. Okay, so today we're going to talk about stratospheric ozone, and we're going to talk about this today and next week after the test, and then maybe a third day. I can't remember. Okay, so remember this: ozone in the stratosphere good, ozone in the troposphere bad. Up high, where we don't breathe it in, it's a great thing. Down here where we breathe it in, it's a bad thing. Okay? So I'm going to talk about stratospheric ozone, okay? How it forms naturally, how we messed it up, and how we fixed it, okay? And by we, I mean the world, right? This is before many of you were born, or I think all of you were born. I was young at the time. So, all right. So we're going to start. We're going to talk about nature. We're going to talk about humans, how these cause problems, and then how we get a solution. Okay. This is usually what happens, right? We kind of think sometimes as whenever there's an environmental issue, it's, Montgomery Burns or someone just disposing of waste, right? That does happen, and those are those things. But a lot of times what we're talking about aren't those clear-cut, horrible things. It's, hey, you know what? We tried to do something good, and we messed up, okay? All right, so let's talk about nature, okay? The ozone layer was first proposed in 1913, okay? They said that they think, or they proposed that in the stratosphere, there was ozone. And they said that this is because we don't see any of this 310 nanometer and below light at Earth surface, right? So they said, hey, it must be ozone in the stratosphere that removes it. A scientist in 1930, Sidney Chapman, came up and he actually proposed how ozone could be formed in the stratosphere. It's called the Chapman cycle. Okay? And it's basically a way that O2 gets turned into ozone and then goes back to O2. That's why that cycle is. This cycle, we'll go through it in a second, is important because it removes UV light. It only occurs in the stratosphere. It only occurs in the stratosphere because for this to occur, you need high energy UV light. Okay? We have UV light down here, but the UV light we have here are in this range, 300, 400 nanometers, right? Still harmful, but not as high energy as below 300 nanometers. All right, so the Chapman cycle starts off with O2. Why does it start off with O2? Because there's always O2. O2 is 21% of our atmosphere, so it's always there. So O2 and UV light with a wavelength below 200 nanometers, so really high energy, tears apart that oxygen. The O2 becomes oxygen atoms. Okay? Those oxygen atoms are obviously very reactive. Okay? They're radicals. So what do they want to do? They find O2 molecules. Why O2? Because there's always O2 around, right? 21%. And they form ozone. So if I sum these two up, right, it is 3O2 plus UV light forms 2O3. Right? One of the simplest reactions you can think about, just one reactant, one product. Okay? So that's how ozone gets formed. Well, ozone can then react with more UV light, which breaks it apart back to O2 and oxygen atom. That oxygen atom, ridiculously reactive. What does it react with? An O2, or sorry, actually in this case O3, to form 2O2. If I sum up this destruction reaction, it would be 2O3 plus UV light goes to form O2, right? You need to have 2 because Wait, what am I thinking? Oh, you have 203. Oh, yeah, you have 3 O2s if you add these two up, right? In the oxygen atom, it gets formed and then it gets destroyed again. Right? So notice, we went from 3O2 to 2O3, went from 2O3 to 3O2, right? Seems like a null cycle. Nothing's happening. But the key thing is UV gets destroyed, right? UV is a reactant. It's not a product, okay? All right, so if I summed up all these, I would get this, right? 3O2, 3 oxygen atoms, 2O3 plus UV light goes to form 3 O2s plus 3 oxygen atoms plus 2O3. Oh, 2O3, 2O3, 3 oxygen, 3 oxygen, 3 O2, 3 O2. Everything cancels out except for the UV, right? This is awesome, okay? Like this just happens naturally, and this is awesome because this allows life on Earth to develop, okay? Our DNA would not, we could not survive with 200 nanometer light, right? Even that would cause skin cancer, right? Life as we would know it would not have developed without this, right? So we have this cycle, right, where 3O2 goes to 2O3, 2O3 goes back to 3O2. This cycle just removes UV light. So the Chapman cycle, those numbers are good to know, right? It removes 97%, 97 to 99% of all UV light, okay? It only happens in the stratosphere because you need this 200 nanometer light to kick it off, right? Down here, we don't see any of that. And now you may think, oh, we don't get any ozone. You get what's called steady state ozone, right? There's a certain amount of ozone there, between being formed and being away, right? All right, so that was Sidney Chapman, right? So it was proposed in 1913. Sidney Chapman came up with the Chapman cycle in the 1930s. Right? But we still didn't know how much ozone there was. You could probably do some studies to figure out how much there is, et cetera. But another scientist around the same time, Gordon Dobson, he came up with a spectrophotometer, right? What's a spectrophotometer? It's a meter for photo, so it's light. Spectra means it can look at different wavelengths, right? He pointed a spectrophotometer at the sun from the ground. And he measured 2 different wavelengths, and the ratio of them told him how much ozone was in the column. Okay, so basically he knew what the absorption was of ozone in a cell, so he could use that to figure out how much UV ozone there was between the surface and space. Okay. All right, so there's it's in northern Canada, so he's looking at everything from the surface to space. Okay. He came up with something called the Dobson unit. Okay. And again, I don't know if he called it the Chapman cycle. I don't know if Dobson said, no, it's my unit, right? But it became known as the Dobson unit. And basically, if you took all the ozone in that column and compressed it down to 0 degrees C in 1 atmosphere, the width of it would tell you how many Dobson units there are. That's weird, I know. But 300 Dobson units is what he said, right? Typically, there's about 300 Dobson units above us, okay? That's not all down here. Most of it's in the stratosphere, but some can be down here, right? Look at this, You didn't know it at the time. We know it now, right? Most of your ozone is in the stratosphere. There's some down here, but most of it is up high. Yeah. They still make these types of measurements, except now they're a lot cooler looking and probably more expensive. And there are a hell of a lot more of these because they have them all around the world. So 1 Dobson unit, 0.01 millimeters if you compressed it all. Right? Oh, wow. So global average is 300 Dobson units. Yeah. This on the left, so he was measuring from the ground. Now we can measure it from satellites. This is the world or the southern hemisphere. And you can see that, okay, if you kind of average it out, it's somewhere around 300 Dobson units. Okay. So for the rest of this lecture, just have that in the back of your mind, 300 Dobson units. Okay, so they proposed it in 1913. 1930, we got this Chapman cycle. And then Dobson unit is the measure of column ozone. And seeing that most of it is in the stratosphere, we kind of say, okay, if the column ozone goes down, it's probably because something's happened in this stratosphere. And it's about 300 Dobson units. Okay. That is naturally occurring. Okay. Questions? Okay. Chapman cycle, ozone layer, good thing. Okay. Let's now talk about humans. We already talked about this, you know, in the 1800s, 1800s, we saw this huge population increase. Okay. Industrial revolution, more people. More people equals more food. More food means you need more refrigeration to keep that food cold or fresh, right? We also have more things, right? We now have cars, which, you know, we want an air conditioning in it. We need other things. So we need, you know, we could just say more refrigeration. So let's talk about refrigeration. Who here has seen Frozen? Okay, who's that guy? Is it Olaf? Okay, what's Olaf's job at the beginning? When he's a little kid, the first scene or first couple scenes, right? He's carving ice out, right? Kristoff, yeah. So Olaf's the snowman. Yeah, sorry. Sorry, my bad. So Kristoff, right? That is how they used to have refrigeration, right? You'd go to a lake, you'd go, to a lake, you'd carve out some ice, you bring it back to what's called an ice box, you put it in there, right? You put it in that one on the top left, and then it kept everything else cool. Okay. It worked, not very practical, right? Here, it's not going to work at all, right? In Wisconsin or someplace like that, it probably worked, but not all year round. Okay. So in the 1900s, they started using artificial refrigeration. Now, artificial refrigeration, you have a gas coil. It's still pretty much the same in the back of a refrigerator, right? You see a bunch of coils, right? If you stick your hand back there, it's really hot, right? What it's doing is it's removing heat from here and taking it outside, right? So you have this gas coil, right? And the gas coil starts off with cold gas, right? That warms up a little bit, right? Then it goes in the compressor, right? And it kind of forces it back out, and you try to get all this heat coming out. Now, what it does is it uses gas expansion. Okay, we're not going to go through it. Sometime I should, right? But think of PV equals nRT, right? What happens if all of a sudden you drop the pressure down by having gas expansion? PV. So if you drop P, your T goes down, right? So if you have gas expand, it cools down. That's what it's doing, right? There's a device there that allows it to expand. All right, so you need gas for this. Well, what kind of gas are you going to use? Well, early attempts were with ammonia, NH3, or hydrocarbons. Not the best, right? Ammonia, toxic, it smells horrible, right? Hydrocarbons are flammable. So you need this compressor down here. What happens if there's a spark? That's not good. What happens if some of these hydrocarbons leak out of the refrigerator and you turn on your stove? Boom, right? So that's not good. So in the 1920s, they developed synthetic gases, right? So totally man-made gases, never before developed, right? In nature, we don't see these. Right? There are some things, in everyday life that we make, right? They make a lot of ammonia. Somewhere there's a plant that makes ammonia, right? These ones we're talking about, so it's natural and also synthetic. These are totally synthetic. Okay? The class we're going to talk about are what are called CFCs. Okay? CFCs stand for the three elements inside of these compounds. What do you think those elements are? Chlorine. Oh, I have it at the top. Chlorine, fluorine, and carbon. Okay? These are, I always spell fluorine wrong, the only elements in there. They were developed by companies. DuPont was one of the leaders in it. Right? They wanted to protect their stuff, so they often gave them code things. So they call them CFC 11, 12, 13. Right? CFC 11 has 1 fluorine and 3 chlorines. CFC 12 has 2 fluorines and 2 chlorines. CFC 13 has 3 fluorines and 1 chlorine. You don't need to know the numbers, the names. It's just, CFC 12 we'll talk about a lot, right? CFC 12 is 2 chlorines and 2 fluorines connected to the carbon. We're going to use it, talk about it a lot because it was the most widely used, and therefore it's the most in the atmosphere. And so we kind of use it just as a placeholder for all CFCs. There are also some CFCs with 2 carbons or with 3 carbons. So for instance, CFC 111 has C2FCl5, right? There are other CFCs. There are CFCs with 211, et cetera, right? All these different types, you don't need to know them, but if you were working at DuPont at the time, you would have all these numbers and you'd say, oh, what works best for refrigerators? This. What works best for air conditioners? This one, right? So they have slightly different properties, right? So they'd be used for slightly different things. Yep. All right, so the trade name for them is Freon, right? So you've probably heard of Freon. Freon is CFCs. By the way, Thomas Midley Jr., that guy on the right, he was one of the people at DuPont in charge of it. He also invented, or he didn't invent it, but he was one of the leaders in putting lead into gasoline, right? So he put lead in gasoline, he put CFCs in the air. We'll talk about why CFCs are bad. They're completely synthetic. They're non-toxic, okay? At one point, someone put like a mask on with the CFC like tank and like breathed it in, and non-toxic, right? Worked great. There was a PBS show, we'll look at a clip of it later, called The Ozone Hole, How We Saved the Planet, right? This was one of the scientists from NASA talking about it. And, He said, these are really wonderful gases, right? If you want to replace ammonia, hydrocarbons in refrigerators, CFCs are awesome. Okay. They're also very non-reactive. Why? Because they don't have hydrogen in them. And remember what we said. OH wants hydrogen. So if you have something without hydrogen, it doesn't react with OH. So it just stays in the atmosphere for a long time. Right? CFC 12 lifetime of 111 years, 11 74 years, 13 90 years. I don't know exactly why the difference, right? Well, probably photolysis, but long life. Okay. I don't know quite why. Yeah. They had a lot of different uses. Okay. Air conditioning, refrigeration, fire extinguishers, right? Aerosol canisters. If you want to make foam, right? Styrofoam, think about it, it's fluffy and it got there. You would put some gas through it, right? CFCs were good because they were inert. They wouldn't turn your styrofoam a different color or make it smell or anything. Just one thing on propellant. So let's say you have some perfume or something, right? How that works is you have a little bit of liquid in there and a lot of propellant in there, these things like CFCs. And when you squirt down, what you're doing is you're releasing the propellant and a little bit of that liquid. Okay? You don't want to have just the pure liquid, right? Well, if you don't have that propellant, it's not going to push it out, right? But also, the propellant's cheap. Whatever that thing that the actual perfume is expensive, right? Oh geez, this is how you do the numbering. I always thought it was cool, but you don't need to know this. But how they did it, there's a long way for how they got the numbering of them, the CFCs. Okay, so we had a lot of sources of CFCs because all of a sudden we were using them for a lot of things. Okay, there were very few sinks. Why? Sinks are things that react. There are not a lot of reactions that remove it, right? They don't have OH, so no hydrogen. So they have a very long lifetime. Okay? This is a plot of CFC 12 versus time for the northern hemisphere in the red and for the southern hemisphere in the blue. 1920s, 1930s, none. Why? Because CFCs are not natural in any way. Okay? All of a sudden, we see this increase. Why do you guys think there was more in the northern hemisphere than in the southern hemisphere? What's there more of in the northern hemisphere than southern hemisphere? China's in the northern hemisphere. India's in the northern hemisphere. US is in the northern hemisphere. Those are the three largest population countries, right? The vast majority of the population of Earth is in the northern hemisphere. So that's why slightly more in the northern hemisphere than in the southern. But not a whole lot of difference. Why? Because it's long enough lifetime that it mixed throughout. Okay. By the way, the scientist who developed this or who studied this was a scientist called James Lovelock. He used gas chromatography, and we talked about FID being flame ionization detection, which is one of the ways, right? We talked about mass spec. He used GC hooked up to an electron capture detector. GC-ECD is really good for measuring halogens. Right? Here's a map of the world, right? You can see that even Africa, we kind of know The majority of people in Africa are in the northern hemisphere, right? All right. So CFCs, oh yeah, well, it mixes throughout the atmosphere, okay? Let's just talk about how lifetime affects how things spread. Here are satellite data of NO2 and CO2. This is in 1 month, August 1997, July 2003. It doesn't matter, right? Notice if you look over New York, right, the northeast corridor, you see red here. That's really high levels of the NO2. You do the same thing for CO2, and there's not as much, right? It's actually off. If you look here, there's no NO2, right? When you have things that are long lifetime, they're able to spread further, okay? Notice, this plot here goes from 0 to 20. So if you go off the coast of New York, like halfway across the Pacific, basically you go from 20 to 0, right? If you go from New York to off the coast, you go from, well, 376 to 380, and then even here you're down to 375. Even if you were to go to the most remote places in the world, down here, you're still at 365, okay? Why? Because things spread if they have a long lifetime, okay? So it's able to spread throughout the atmosphere, even to the stratosphere, okay? So it's not just that the CFCs spread in X and Y, they also go in Z, right? They go up in altitude. Okay. All right, so let's remember, we have the ozone layer, we have the Chapman cycle. Awesome. Removes 97 to 99% of all the UV light. Great. We have CFCs. We use them for refrigeration. Because we use them for refrigeration, their levels increased. They got all over the world. CFCs are also great. Okay? How can it be if we have two great things, them coming together can form something that's bad? Well, let's talk about that. Any questions so far? Let's talk about the problem. Two scientists, Dr. Rowland and Dr. Molina, they were both at UC Irvine. They won the Nobel Prize in 1995 for this work. Okay. In 1974, they wrote this paper. Right. This is what got them the Nobel Prize. And follow up, but I think it's 4 pages. Right? If you look at it, like 2 figures, right? Not a lot, right? But stratospheric sink for chlorofluoromethanes, CFCs, right? Chlorofluoromethane is a methane with chlorine and fluorine, so CFCs. Chlorine atom catalyzed destruction of ozone. Okay. So what they said was this. If you have a refrigerator, right? This is the 1970s, so it's not as nice as that. But if you have a refrigerator, that refrigerator has CFCs in it. Those CFCs will eventually leak, or when you get rid of the refrigerator, those will just be released. They make their way to the stratosphere. This takes a long time. It takes about a year to go from the troposphere into the stratosphere for gases, but CFCs have long lifetimes, so they can do that. Once in the stratosphere, you have high energy UV light. So if you have UV light that is lower wavelength than 290 nanometers, so higher energy, it can take CF2Cl2 and it can break apart a chlorine. Going to pass around attendance. Anyone need the study guide? Air quality lab's also there if you need it. All right, so we have these chlorine atoms. Okay, chlorine atoms are formed. They're very reactive. Why? Because they're radicals. So those chlorine radicals, I'll write them down and then I'll put them thing. The chlorine radicals are in the stratosphere and they need something to react with. Well, they can react with ozone. They take and they form ClO and O2. So basically, they remove an oxygen from the O3, right? They form O2, which is very stable. ClO is still a radical. So if it's still a radical, it's not going to just stop. It's going to have another reaction. Well, it can react with another ozone. And if it reacts with another ozone, it can form Cl and two O2s. Here, actually, the ozone is taking away the oxygen from the ClO. So I have these two reactions. Okay. All right, on your piece of paper, right, add up these two reactions, right, and tell me what the final reaction, the overall reaction is for these two reactions combined. So I have a chlorine, I have a ClO, I have two O3s, I have a chlorine, I have a ClO, and I have three O2s. So the chlorine cancels out. The ClO cancels out. So I have two ozones going to form 3O2. Okay. What is it? What is the name for a compound, in this case chlorine, that speeds up a reaction or allows it to occur, but doesn't get used up? It's a catalyst. Enzyme if it's in the body, right? So this is a catalyst, right? The chlorine, in this case, is a catalyst. One CFC molecule, which can produce that chlorine, can destroy hundreds of ozone molecules. I don't think, hairspray is not as big a thing. Back in the 80s, it was like, oh, hairspray. I remember my dad, right? But like you put a hairspray, right, producing that chlorine gets everywhere, right? That gets everywhere. And then once it gets up there, it destroys that ozone. Okay. All right, so that's what they proposed, right? Roland and Molina, they proposed these reactions. that can do it, right? You can see it in their paper, right? Cl plus ozone goes ClO. ClO plus O gives you that Cl, right? DuPont has made money off of CFCs. They said that this is a science fiction. So that was 1974, 1975. A science fiction tale, a load of rubbish, utter nonsense. Okay. Always remember $8 billion they're making in the 1970s, right? In today's terms, that's something like, I don't know, 40 billion, 50 billion, I don't know what it is, but more than I make, right? All right. What did Rowland say in response in 1984? Nothing will be done about this problem until there is further evidence that a significant loss of ozone has occurred. Okay. Unfortunately, this means that if there is a disaster in the making in the stratosphere, we're probably not going to avoid it, right? Going to the doctor every time, and they say, you need to lose weight, you need to lose weight, you need to lose weight, waiting for that heart attack before you say, hey, maybe I need to lose weight, right? Maybe I need to take care of myself. That's what he said. Well, unfortunately, Rowland was kind of wrong here, right? Fortunately, we were able to do something before that disaster. Okay. All right. So let's look at, so far actually, Rowland was just proposing this. Rowland and Molina were just proposing it, right? Rowland was the Molina's advisor, right? Molina was a postdoc. That's why I talk about Rowland more than Molina. So this is a plot from satellite data of ozone from 1980 to 2000. The different colors are different satellites, okay? Because the satellite can't stay in space forever, right? Well, in some cases it does, but it dies, right? Most of them crash into Earth, but some just like float out there. So these are the different ones. What do you guys see? So if I showed you this data, tell me what you see. Right? Ozone decreasing, anyone want to say? Is it always, what we call monotonically? Have you ever heard monotonically decreasing means it's always decreasing, right? My weight seems to be monotonically increasing, right? Technically not true, right? Is this monotonically decreasing? Is it always decreasing? No, right? You see even in 1 year, you see some variability, right? It's going from, 290 here to 305 down, up, down. So it looks like it's almost a yearly cycle, right? Kind of like the ozone we were looking at earlier, tropospheric ozone, right? Up and down. There's this part, kind of decreased, then went up, and then it went down, But if you did a yearly average, you'd probably see a decrease, right? Notice, sometimes when you look at data, sometimes it's good to just say, okay, let's look at the extremes, right? Look from 1980 to 85, it almost always got above 295, right? At some point during the year, it was above 295, right? Here it got up to 305, 302, 304 maybe, 302. Here it got to 298, 298, all these. By this last period, it never got above 295, right? You're not seeing those extremes anymore. And you're starting to see the extremes in the other way, right? The first 5 years of this data, it never got below 285. Here, it's always getting about below 285 every single year, okay? So, sometimes in lab, we go for this beautiful picture and all this data. A lot of times it's not as pretty, right? You kind of have to look some ways to do it. All right, so overall, a 3 3% decrease in the ozone layer, right? So if you go this to this, okay, about 3%. 3% out of 300 is 9 Dobson units, right? So about 300 down to 291. Sounds about right. There's seasonal cycle, year-to-year variability, but we're seeing it, okay? Is 3% decrease something you're gonna worry about? Maybe. I know no one wants to get 3% less money, right? But you're not necessarily gonna be homeless if your paycheck goes down by 3%, right? But still some reduction. But if we look at the southern hemisphere, we do see a huge decrease. At the southern hemisphere, over the Antarctica, we see up to a 70% decrease. This is known as the ozone hole. Okay, this is an image from September 1987 of the total ozone in Dobson units. What did I say was good or normal? 300, right? 300 is this greenish, right? Green to yellow is 300, right? Here, over the South Pole, it's getting down, and I see some purples, like 100 to 200, right? It's really huge reductions. Okay? This ozone hole happens in Antarctic spring, okay? Remember, the southern hemisphere is the exact opposite from us. So when we have summer, they have winter, right? When we have fall, September-ish, they have spring, okay? And in the southern hemisphere, if you're in this region, your winter, our winter is not that bad, right? Oh, a little less sun, thing. Their winter is total darkness. So they're going from total darkness to now having sunlight and UV light. Okay. So here's just an image from March 1987 to September 1987, right? You can see predominantly green, maybe to the aqua, so maybe a little below 300 to this huge thing, right? This is from July 1st, 1987 to December 31st, 1987. Yeah. So July, green, maybe we're a little below green, but if I were to average this all up, I'd say it's below 300. Let's look at what happens. Notice the circular, that's that polar vortex, right? Winds kind of go in a circle. Okay, in August, you start seeing some purplish, that ozone hole forming. Then in September, bam, there it is. October, still there. We're seeing some really low, some of these cases it's down into that 100 level, right? Magenta. November starts to break up. December, it starts to look back to what it was before. Okay. All right, why do you think this is the case? Any thoughts? Why are we seeing this ozone hole in spring and only over Antarctica? What's the difference between Antarctica and the Arctic? You can stand on the South Pole and you will be on ice, but below you is some land. Is that the same at the North Pole? No, the North Pole, you can stand there because it's sea ice, right? But if you drill down, I don't know, 20 feet, you'd get into the ocean, right? The South Pole, you have this huge landmass, and that landmass is covered in ice. So it's like having an ice cube there. So Antarctica is colder than the Arctic, okay? Because of that landmass. And this polar vortex circling around Antarctica, kind of traps all that cold air in, okay? And so, because it's really cold, you can get formation of what are called polar stratospheric clouds. These are clouds in the stratosphere and only over polar regions. They only occur when it's really, 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 really cold. Okay? These clouds are actually different. When we were talking about aerosols previously, we said every cloud has a particle at the center. Not these clouds. These clouds are pure water, or actually some acids in there, but they have no particles there. They're ridiculously pretty, right? This is a picture. These clouds are all in the stratosphere. They're really high up. This is from McMurdo Station, which is on the coast of Antarctica. Looking up, they're high altitude. And a scientist called Susan Solomon, who I think is now at MIT, she was one of the first ones to propose this. And because you have these clouds, you have on there heterogeneous chemistry occurring. What does heterogeneous chemistry mean? What does hetero mean? Different, right? Not different compounds, different states. So now you have a solid, or a liquid, actually, that cloud, and you have the gas phase allowing for reactions to occur on there, okay? And so what these PSCs, those polar stratospheric clouds, do is they're a reservoir or a bank for this chlorine. Remember previously we said CFCs form, they get up there, they form chlorine, that chlorine destroys it. What happens is that chlorine can basically be stored on those clouds. And then once you have this UV light coming from the spring, that releases a whole bunch of chlorine all at once, and it destroys a bunch of ozone all at once. And so that's why you see these polar, the ozone hole, because of these polar stratospheric clouds. Those clouds kind of act like, platinum. If you have a reaction, you put platinum in there, it's a catalyst, right? It's a place for these reactions to occur. PSCs, in order for them to form, it has to get below -78 degrees Celsius, so really dang cold, right? On the top, this is 65 to 90 degrees north, so the Arctic. On the bottom is the Antarctic. Notice in the Arctic, the temperatures only get down that low for maybe a month, right? Whereas, and really it's the green line that's the average, right? In the southern hemisphere, it's below this temperature from around May all the way to October, right? So these really cold temperatures allow those clouds to form. All right. So Roland and Melina proposed this. Okay. Susan Solomon and others saw, or no, Roland Melina proposed it. Satellites showed this ozone hole. Susan Solomon said, hey, maybe it's these PSCs that are forming it, right? It wasn't until 1989 where they actually used flight data. They flew what's called an ER2, which is the military has what's called a U2, which is spy planes, right? They're very long-lived, they long wings. They fly, 40,000 feet high, and those are the ones they fly over, China or North Korea or all that, high enough that they can't be detected. NASA has what are called ER2s, which are the civilian version. So they flew that over the South Pole, and notice what happened. Here's what they saw. Ozone, as they flew from 62 to 70 degrees south. Ozone was fairly constant and then decreased. Meanwhile, the COO they measured increased at that same time. And look at these wiggles. Here was a portion where ozone decreased faster and CLO increased faster. So we see this. This is something they call the smoking gun, right? So this basically showed that it was CLO, right? And at the same time, they were doing sampling in Antarctica where they were putting balloons into the air to try to understand what was happening. Okay? And so this is now going to be a video of September's, right? September is kind of when the ozone hole was the worst, from 1979 to 2016, okay? So 1979, we're seeing maybe in the 280, 250 range, okay? Let's look at it and see what happened. Okay, so 80s, 90s, now you're seeing those purples, right? It's growing, right? We're seeing that hole getting bigger, right? And more sustained. What they could do is they basically looked at it and they looked at an edge, and I don't know what they did. I think it was if it's below 200, they said, okay, that's the ozone hole. So in this case, they basically said, okay, where is it? This dark blue. Not having a good circle, but that's the area of the ozone hole. Okay? And so the ozone hole from 1979 to 1994 grew to 24 or 25 million kilometers squared. Okay? I don't know what that means, right? Is this a million kilometers in this room? I don't know. Basically the size of North America, right? So the ozone hole grew from being tiny to being the size of North America. Okay? All right, now, we'll get to this in the future. If you don't stop anything, there's no reason to believe it's just going to magically flatten out, right? If it stayed this big, right? Let's go to the end. Right? If the ozone hole stayed this big and only over Antarctica where there are penguins and maybe some researchers, maybe not that big a deal, right? I like penguins, but whatever, right? But if you don't change anything, there's no reason to believe it's magically just going to stop, right? There's no reason for us to believe that this isn't going to just keep on growing until it covers the entire southern hemisphere, right? Yeah. There's no reason for me to think if I don't change my diet, if I don't change my food, I'm going to stop gaining weight, right? Okay, so studies showed, or modeling, for every 1% decrease in stratospheric ozone, you get a 2% increase in UV intensity and 2 to 4% increase in skin cancer. Okay, so remember, what did I say when we showed this? What percentage decrease? 3%. So 3% decrease already is 6 to 12% increase in skin cancer. Not good, but 10% more chance. Well, if it keeps on going, that was in 20 years. We're 20 years past that. Maybe it would be now 6%, 12%, now a 24 to 48% increase in skin cancer. That's pretty bad. Okay? All right, so we talked about the ozone layer. The ozone layer is a good thing. Actually, let's say a great thing. CFCs were a good thing. We used them in a lot of things. We used them in the cars. We used them in refrigeration. Unfortunately, we got this ozone depletion. Okay. Next time we're going to talk about the solution. But what do you guys think the solution should be? Let's say we're in 1985. What should we do? Stop using CFCs. Okay. It's kind of like that old joke, hey, doctor, it hurts every time I do this. What does the doctor say? Stop doing this, right? If CFCs are causing the problem, let's get rid of the CFCs, okay? Now, we'll talk about that. That ended up being the answer, right? Now, let's just real quick, I'm sure I have slides later on, but let's just put this point now, right? I'm going to have the same thing when we talk about climate change, right? Hey, climate change, we produce CO2, or, we produce CO2, that causes an issue. What's the solution, right? It's easier to remove CFCs, right? But CO2 emissions, which are the reason for climate change, are a lot harder. Why? Because to cut out all CO2, you guys turn on all your cars, right? You stop electricity because 80% comes from burning fossil fuels, right? So while this is awesome and good, it is much, much harder once we start talking about climate change, okay? All right, we'll talk more about this next time. Any questions before we go? All right, let me, so the air quality lab, I think, is due on the 21st. So you still have time. Any questions? Okay. Some of you have already started, and that's awesome. If you haven't, right, I suggest you start now, so that way you can do some, ask questions. Let me just pull up Excel really quick. How are you guys? One of the things I ask is how many days were above 75 ppb, right? How did you guys find that? Okay. So one way is, so let's say this is day 1, 2, oops. Let's say I have this data and I said, so I have 80, 54, 64, 90, 32, 84, right? If I want to know how many of these days are above 75 ppb, one of the things I could, or 70 ppb, I don't know what I asked. What I could do is I just could go down and I could do 1, 2, 3 days, but you have to do this for 365 days. It gets annoying. Excel, and I harp on this partially because I don't know what you guys are going to do in your life, but even if you work at, manager of a Starbucks or whatever else, you're probably going to use Excel or something like it, right? Always think if you're doing something like this takes a long time, go on Google and say, is there a quicker way to do it? Because there is in a lot of cases. In this case, you can use something called, I'm good at using Excel, and I can do stuff like this. Excel is kind of can do lazy coding, right? It's not coding, no thing, but you can do a lot of things, right? In this case, you can do average ifs, and I'm going to choose this entire column, and I'm going to say, oops, not average ifs. In this case, it's count if. Count if. So I'm going to do this, and my criteria is if it is above 70, right? It's a little bit weird. You have to do the greater than in quotes and then use the and it comes back with 3, right? So I can do this if there are a whole bunch of them, right? So just one thing, if you're, have some time, you can do count ifs. If you wanted monthly average, you could use average if, right? Stuff like that. Right? Or you can just count it by hand. That's fine. But sometimes if you had to do this for 12 years of data, that'll get annoying. All right, any questions on satellite or the AQ lab? Yeah.
How do you put like little boxes for the dates, so for mine, I have 2019 is orange and then 2000.
Oh, you want a legend?
Boxes, yeah, how like the dates.
Are you talking about, I'm just gonna have some, oops. Something's weird with my Excel, okay. I'm making up data. Okay, so these are my two graphs. You mean you want this right here? The legend, okay. So it's not on yours, right? So yours looks kind of like this. What you can do is add chart element, okay? You're using thing. It's probably something similar, right? Add chart element, in my case, it's a legend, right? And I can say where to put it, right? And then I can change the name of these.
Yeah, it's called legend.
Okay, yeah, so, cool. Cool, any other questions? All right, I think next Thursday, we're actually gonna start on a satellite lab. So we're gonna look at some satellite data. All right, cool. If there are no questions, I will see you all on Tuesday. Remember, Tuesday is the midterm, okay? See y'all later.